Welcome. We're going to be doing Physics 220, lab number 7, the magnetic force on current lab. The equipment for this lab is right here. So we have a coil of wire which is connected to a power supply back here. And so we can just pump current through the wire. We've just got a horseshoe magnet here which we can raise or lower. Raise and put it into the wire. And then when the current's on, we're going to see there's going to be a force pulling down on the coil, and we're going to be able to measure this force through the force sensor, which is right there and connected to the computer. In order to predict what that force would be, we need to know the magnetic field inside the magnet, and so we're going to be using a Hall probe to measure that. So this Hall probe, we can just insert it, and if we step down on the foot pedal to give it some power, it will record the magnetic field, and it records it. The output of this is just a voltage, which we're measuring here and plotting on the computer. But if we multiply it by 1.5, we can take that voltage and convert it to Tesla. And we're actually going to do that automatically on the computer. So this is a software file that we're going to be using. We set this Hall coefficient to 1.5 so that whenever we take a measurement, it'll just automatically adjust it so that we're plotting the Teslas, the magnetic field, instead of a voltage. The nice thing is that there are little tick marks on the Hall probe here that are each spaced for 1 centimeter. And so we're just going to start at 0 centimeters and then go to 1, 2, 3 centimeters, and then that's how we're going to plot the position. And at each point, we'll just activate the Hall probe, and then on the if we hit the data collection, when I activate the Hall probe, we'll see this little point here, which is plotting the magnetic field there. And so what we can do is just hit keep, and then it'll let us put in the position. So right now we're at 0, and so it plotted that point there. And so what we can do is just move in. I just moved in on the Hall probe here for 1 centimeter to the next one, so it's just a centimeter closer in. And again, I'm just activating it, and we see that this is where it's showing up. So I'm going to just hit keep, and then I'm going to plot this in centimeters because that's what we're measuring, but the units here are meters, so I'm just going to do 0.01, corresponding to 1 centimeter, and then it's up here. Okay, and so I'm just going to go ahead and move the probe in so that it's now at 2 centimeters. And I might adjust the scale here so that it's easier to see. There we go. Let's see, so probably I'll just do 0.1, 10 centimeters. Okay, that's a little bit better. Okay, so here's the new point. Again, we're at 2 centimeters. And so we'll put that as 0.02. And you should be plotting these points on your graph here, right here, as we go along. This graph here is where you should be plotting these. And I'm going to go ahead and move in the Hall probe again. And there's our new point. Now we are at 3 centimeters. Okay, I'm going to move in again. We're now at 4 centimeters. Okay, and we'll move in again. So we're at 5 centimeters. And you'll notice it's leveling off as we're in the inside, kind of the central point of the magnet. We're now at 6 centimeters. And here is 7 centimeters. And 8 centimeters. So you'll notice it started to go down a little bit, and if we look here, we can see that the Hall probe is just exiting the magnet. It's still in the center, but the tip is starting to get outside. So here, the magnetic field is no longer uniform between the plates, and it's starting to decrease. Okay. Now we're at 9 centimeters. And we're at 10 centimeters now. And I might adjust this scale a little bit. Move out to 11 centimeters. And we'll do one final point at 12 centimeters. Okay. So there's the plot of our magnetic field versus position as we went through the horseshoe magnet. You could manually integrate this by kind of counting squares on your own plot, or we could, what I'm going to do is let the computer do it for us. So there's an integrate function where it's going to numerically evaluate the area under the curve. And so we have 0.006549 decimeters. And so right there is that integral. So what we just did is integrate the magnetic field over the length. So this integral of b dl is what we just performed. And that's that value that we just showed you. And so the next part is we're going to want to predict the force. And so we have these other two things that we need to record. So one is the current, and then one is the number of loops in the wire. And so it's labeled here. We have 500 turns. So this wire coil, I guess, loop, it has 500 loops of this thin wire. And so that capital N is 500, and in the current, we're going to try to set to be 300. And so let's go ahead and go on right now. So everything's still zeroed from before. So what we're going to do is turn on the current here. And you'll notice that we're pretty close to, at least within 3 digits of 300 milliamps. So 299.5 really, but we're pretty close. And so that's our current there. And then here, so from this current, you should be able to mathematically derive the force that we would expect to see on the coil. This force is not it, because the coil right now is kind of just on the top of the magnet here. But what we're going to do is, after you've derived that force, is we'll raise up the magnet. So now the coil is approximately where we were measuring the magnetic field before. I'm just going to take this out of the way. So we measured the field on the magnet at about this height, and now we're sending current through the coil, and it's at that same height. And we can see the force now is 0.97-ish newtons. And it's negative because it's pulling down right, but we really only care about the absolute magnitude of the force, so you don't necessarily need to put that. But that is the actual measured force, and should be somewhat similar to the predicted force that you got from mapping out the magnetic field. So that's it for part A. For part B here, pretty simple. We're just going to vary the current and then make sure that the ratio of the force over the current doesn't change, because we're not changing the magnetic field at all, or the number of coils or the number of turns in the wire. And so we already have the force for 300 milliamps. So you could just divide that force by 300 milliamps, and we get that ratio there. Let's go ahead and go down to 200 milliamps, or approximately. It's pretty close. Could probably go with that. So 200.8 milliamps, and that gives a force of 0.647 newtons. And so, and for our final point of data, we're going to turn this down to 100 milliamps, So I'm just adjusting the current on the power supply. It's probably close enough. So 100.6-ish milliamps. You have a force of 0.325 maybe, kind of in the middle there. And again, you just have to divide this by that, and then you get these ratios that it's asking about here. And then you can find the percent difference between the largest and smallest, and it should be pretty small because that ratio should be consistent. So, thanks for watching. That's it for lab number 7.